Yes. Okay. The next speaker is Veronika Hubeny from UC Davis. She's gonna tell us about holographic entropy cone from marginal independence.
Okay, well, thank you very much. It's a pleasure to speak at this meeting, and congratulations for the Extreme Universe. So this will be about work that has appeared in the past as a bit of a review and mostly work in progress with these wonderful collaborators. And I should say that the main drivers of this project has been Max Rotta, and Sergio Cuenca has contributed enormous amount as well, and they're both on the market this year. And they're both excellent. Sergio is a student in UCSB, and Max Rotta is a postdoc at Amsterdam. Okay, so let me start. So the motivation, broadly speaking, is to ask, how does, in holographic context, how does actually gravity emerge from the non-gravitational dual? And we have seen many hints that entanglement structure somehow seems to be playing a crucial role. And so the motivation for the project is to characterize the aspects of sort of entanglement structure that define for us or delimit geometric states. By which I mean states in a holographic field theory, which would be described, or which would describe a classical bulk geometry. Now, what I mean by this entanglement structure is a bit more obscure, but what I really mean is just structure in entanglement entropy of subsystems. And so this is already interesting from sort of the quantum information theoretic perspective of understanding what type of information quantities are naturally derived from relations between subsystem entanglement entropies. So the broad plan is to go quickly sort of review the previous work, and then to describe the work in progress. There's sort of two key constructs that we have, geometric constructs, which I'll call this Vspace and pattern of marginal independence, and then explain two sort of tools that we use to understand these constructs, basically graph models, and then get to this later, changing the number of parties. And then finally sort of try to describe the main result. So I should say, I don't have a good feel for how comfortable people are with various of these things. So you should feel very free and welcome to speed me up or slow me down, interrupt me with questions. I'll accommodate myself to at least say that the final result, no matter how slow I'm going till then. Okay, so well, this you all know very well. Okay, we'll entanglement entropy being von Neumann entropy of the reduced density matrix, where you have a partitioning of the Hilbert space, and we'll treat the holographic system this way, even and sort of ignore the subtlety about this non-factorizability and so forth, as is quite often done. Okay, so we'll imagine that, okay, we'll decompose our field theory into n subsystems, some number of subsystems, and we'll imagine the Hilbert space is factorized. We will choose this in the holographic context to be spatial regions on which of the space on which the field theory lives. And we'll call these subsystems, we'll label them by I'll use the terminology color, that just means a label. Okay. Now you can consider any mixed state on such a subdivision, and you can also think of that as being purified by some other subsystem. So one can equally think of a mixed state on this n-party system as a pure state, purification of a state on n+1 party system. Now, given such a subdivision, we can now specify entanglement entropy of any of these subsystems. And similarly, we can specify entanglement entropy of any composite such subsystem. And so there are 2 to the n-1 independent entanglement entropies corresponding to this subdivision. Basically, you can, for each of these, you can determine whether that subsystem is included or not. So that's how you get this, and but you don't want everything being excluded. That's how you get this part. Okay, so there D 2 to the n-1 numbers or quantities that describe the subsystem entanglement entropies. So if you have just 3 parties, 3 subsystems, then we can arrange them into this 7-dimensional vector in entropy space, where I just list all these individual entanglement entropies. Okay, now when we have a holographic subsystem, it's useful to, holographic system, it's useful to utilize this ability of describing small subsystems that are arbitrarily really small, because the field theory lives on some continuum, and I can partition that continuum as much as I like, up to at least some UV cutoff. And so we would like to imagine that we can explore this entropy space when it is very large, when I can have a very refined partitioning. And I want to ask what sort of an entropy vector can I get on this huge space? Okay, so not every entropy vector is, of course, allowed. For one, all the entropies are non-negative, and therefore we're restricted already right from the start to the positive orthant. But we have more restriction than just positivity. Matt already mentioned one in his talk earlier, which is, or for you last night, which is the relation of sub-additivity, which you can think of as just positivity of correlations between subsystems, or non-negativity of correlations between subsystems. And also the strong sub-additivity, which you can think of as sort of monotonicity under inclusion of this correlation, or positivity of this conditional mutual information, which just says that if you have 2 systems that are correlated, as you enlarge either one of them, that correlation can decrease. Okay, so those are both very sensible statements, and in fact they are completely universal statements about any quantum system. So the set of possible entropy vectors is certainly restricted by relations of this type, but it's also restricted by further relations depending on what system I'm actually talking about. And what we want to do is talk about the system that is describing a geometric state in holography. So just to step back, how do we want to characterize this object, the set of entropy vectors that are admissible? Well, it's naturally characterized by a region of this entropy space, and it happens to be a convex region, which is a convex cone in entropy space. So the set of all physically allowed vectors for any sort of subsystem forms a convex cone in entropy space, and you can usefully characterize it in a variety of ways. One such way is to characterize the cone by its extreme rays, so that the cone is then a convex hull of this extreme rays. So here's a cartoon, well, for just 2 parties, so 3-dimensional entropy space, and you have these vectors that any positive combination would determine would describe any vector inside this cone. Alternately, you can describe a cone as an intersection of half spaces, which are which are defined by these facets. So for example, if you have a relation between these entropies, which was the subadditivity, well, then it says that the combined entropy has to be no larger than the individual entropies. And so that sort of tells you that you're below this plane, and there are other hyperplanes in this entropy space, and the set of them form half spaces. The oriented hypersurfaces form half spaces, and the intersection of those half spaces is this cone, or what we dub the polyhedron. Okay, so these defining regions on these hyperplanes are what's called facets. You can also specify the cone by some intermediate dimensional objects. Well, for 3 dimensions, there is no intermediate dimensional objects, but if you imagine a higher dimensional entropy space, this is codimension, the facets are codimension 1, so d-1 dimensional. Extreme arrays are 1 dimensional, so there's a whole tower in between. Those things are called faces, and you could also imagine just specifying the cone by some intermediate dimension faces. Okay, we're not going to do that because it's not proving particularly convenient just yet, but you can bear in mind that there's a whole set of specifications that one could in principle use. Okay, so when we restrict this set of the physical systems to a holographic one, well, then this was what was constructed in this paper here and dubbed the holographic entropy cone. Okay, so what is known about this holographic entropy cone? Well, if you have, of course, the set of all geometric states in a holographic field theory is a very small subset of all quantum states. But nevertheless, if your partitioning of the system is so coarse-grained that you only have 2 parties, then it turns out that this quantum entropy cone actually coincides with a holographic entropy cone. And it's the picture that I drew before. It's only composed of this subadditivity and its cousins that are obtained from it by symmetry, by purifications, where you imagine that, well, you can deal with this composite system as just another subsystem, and you can then exchange, you can treat all of these on equal footing. Okay, so there are 3 of these hyperplanes, these facets, which consist of the subadditivity and the Araki-Leap inequalities, and that's it. That specifies the entire quantum entropy cone and the holographic entropy cone for 2 parties. Now, for larger number of parties, for further refinement, the holographic entropy cone is strictly inside the quantum entropy cone. It's specified by more inequalities. So first let me describe the quantum entropy cone and then restrict that. So the quantum entropy cone is specified by, well, the inequalities that Matt already mentioned in his talk, namely the subadditivity. And now we have various different instances of it, because you can you have 3 parties, so you can have subadditivity for A and B, A and C, and B and C, and the purification. So there's 6 such things. But there's more. There's also the strong subadditivity, and so that provides additional facets. Now, I should say what I'm drawing here is not really the full cone. Now you have 3 parties. That means you have a 7-dimensional entropy space. And I'm drawing some, the sketch is supposed to correspond to some 3-dimensional cross-section of the 7-dimensional entropy space, which is not going through the origin. So if I go back to this polyhedron picture, it's like the analog of this blue triangle. Okay, what I'm drawing in this sketch. Okay, so this is like this analog of the triangle. The origin of the entropy space is not shown here. Okay, but the polyhedron now is this 12-faceted object for the quantum entropy cone. For the holographic entropy cone, this is smaller, as I said before. And in fact, the strong subadditivity inequalities become redundant. There's a stronger inequality that restricts the cone further, which is this facet, which is the monogamy of mutual information. And in fact, that's completely permutation and purification symmetric. And so there's only one of those things. So what is that? So just to remind you, these were the inequalities that we saw before. And now this new one, this monogamy of mutual information is, well, in terms of the entropies, it looks like this. It's something that's sort of somewhat similar to these, but more physically, you can think of it, well, it's a negativity of tripartite information, but what really it is this monogamy of mutual information, in the sense that if you have, if you look at the amount of correlation between, let's say, A and the combined system B and C, well then by monogamy of entanglement, the statement is that the correlation between just A and C cannot be recycled by the correlation between A and B, and therefore this quantity has to be larger than the sum of these quantities. Okay, so that's why you get this relation. That's the sort of the intuition behind it. Now, as Matt mentioned earlier, the geometric proof of this monogamy of mutual information in the holographic context is almost identical to the geometric proof of strong subadditivity. And nevertheless, this monogamy of mutual information is actually not applied to all possible, it does not hold for all quantum states. It's easy to find counterexamples of quantum states which violate this inequality. But nevertheless, the geometric proof based on extremal surfaces doesn't discern that, doesn't discern this difference that this inequality is universal, whereas this one is highly non-universal. But it's actually quite nice to see that if you use this bit thread formulation that Matt was describing, that one sees, you can prove both of these in the bit thread language, but the proofs are very different. And in fact, the proof of this MMI is much more rooted in bulk locality than this inequality, which to me suggests that somehow that reformulation of the holographic entanglement entropy is somehow more going to the heart of how these things work, or distinguishing the holographic context. Anyway, that was just a throwaway remark for the aficionados. The main point of this slide was just to show you this relation. And you can see already from here that this strong subadditivity becomes redundant, because you can take the sum of this and this inequality. Okay, that's still an inequality, and what you get by canceling terms is something like this once you flip B and C. Okay, so that's why this inequality no longer needs to be there, because it's already automatically captured by these two. Okay, so that was the story for 3 parties. For 4 parties, things become more complicated. The quantum entropy. Oh, yes.
Can I ask a basic question? Yeah. What exactly is the condition for holographic entropic cone?
Good. That's precisely what we're trying to find. Okay, so we don't know for. We have now described the holographic entropy cone up to 3 parties, and it's described by saying that it's all these entropies. So there's entropy for A, B, C, A, B, B, C, A, C, and A, B, C. Okay, that's all these 3 quantities that are restricted by 7 inequalities. So there's 7 facets. There's 1 inequality like this, and then there's 6 inequalities like this. And that specifies the entropy cone in terms of the facets. You can also describe the entropy. Maybe I should go back to the picture. So those were the 6 were these facets here, and the MMI was this blue one. You can also describe it by the extreme rays. The extreme rays on this picture would be these vertices. Those would be the 6 bell pairs and a 4-party perfect tensor state. Okay, so those that would be specification of the holographic entropy cone for 3 parties in terms of the extreme rays.
So by holographic entropy, you mean the one given by the minimal surface? Is that the definition?
Correct. Good. Okay. So I have skipped this very quickly. So indeed. So we have partitioned the CFD space into spatial regions, any sort of spatial region, and we asked what are the constraints on the entropies, holographic entanglement entropies for those spatial regions. We're assuming we can use just the holographic HRT basically, or any of the reformulations. And we are working in a regime where that is meaningful. So one thing I didn't say, I should have said earlier, is we're thinking of just a regime in the holographic context where we're taking the classical bulk space-time, okay, and if it's time dependent, it has to obey the requisite, energy conditions and so forth. So it's some physical space-time that has a holographic dual in the CFD, and in such a case, we can apply the holographic entanglement entropy prescription, whichever one we want. We compute the, let's say we do HRT, we compute the entanglement entropies by areas of these surfaces, and we say, well, what kind of a entropy vector can that have? And we do that for any dimensional space-time, any set of regions in any physical state. And the set of all of those things live in a subspace in a subregion of the entropy space, which is precisely this holographic entropy cone.
Okay, thank you.
And we are sticking to this large rank of the gauge group, large lambda, large n regime, where we have just really the classical bulk space-time given by that regime. Okay. Good. Other questions now that I
can I ask you one question? So here, I guess by definition, the holographic entropy cone is a necessary condition for holographic theory. But if you take n to be sufficiently large, do you expect holographic entropy cone is also the sufficient condition for holography, or?
No. Okay. I mean, it depends on what you mean by the holographic entropy cone being sufficient. So each configuration and state that I get to specify would correspond to some entropy vector within the cone. Now, if I just give you a state and it happens to have an entropy vector that lies within the cone, that doesn't by itself necessarily imply that that state is holographic. So you can have, as I said, bell pair would be, one of these vertices. Well, bell pair by itself is certainly not holographic, but it has an entropy vector that lies, well, in this case, on the boundary of the cone. Okay, you can take some positive combination of these, a general, 4-party graph, let's say combination of bell pairs and perfect tensor would be somewhere inside. And that itself also is not holographic. So it's not just because the entropy vector is inside the cone doesn't mean that that state whose entropy vector we're computing is holographic. On the other hand, if you have some way of describing somehow the whole set of them, then you might find a specification that somehow knowing that the whole set of them is precisely within this region, then maybe you can find a formulation where you can sort of recast it into some sort of a necessary condition. But I don't know how to, that would require much more sophisticated specification.
Okay, thank you.
Good. Other questions? Okay. So far I described up to 3 parties. This gets more complicated very quickly. For 4 parties, the quantum entropy cone is actually not known. Okay, it's still within a cone specified by the strong subadditivity and strong subadditivity, but we believe that there are many other universal relations, but we don't know what they are. And this is actually one of the sort of important problems in quantum information science. But in holography, we're much better off. We know the cone fully. And in fact, for 4 parties, we still have the facets only given by subadditivities and now several different types of monogamy of mutual information, because now we have more parties, so we have more ways of combining the various subsystems. So now we have sort of 20 independent inequalities, but they're all of this form that we have seen. For 5 parties, we now get new things. We get 5 further types of inequalities. And so they're the previous ones that we had and these 5 new ones. So that combines into sort of 8 distinct orbits, meaning types that generate new ones under these permutations of the subsystems and purification. So in total, there are sort of 372 facets and there are some 2000 something extreme rays. So that's just for 4, the cone for 5 parties. For 6 parties, that cone is not yet even known. There's already many facets known and many extreme rays known, but the story is not complete. So these folks have found a systematic sort of algorithmic way how you would actually solve it, and you know the number of facets that we know about is growing, but at some point the facets specified by inequalities become rather complicated. And what's the key question is really, how do we characterize all of them? And how do we understand what these more and more complicated inequalities are actually telling us? What is the physics of it? So it's no good to generate, you know, millions of these inequalities if they look complicated and we can't do anything with them. So the whole motivation is to sort of try to understand what are they actually telling us. And once you go beyond this monogamy of mutual information, there isn't a very nice narrative of what of all these other inequalities actually are telling us, because they're much more complicated. Okay, so what do we do about describing the holographic entropy cone for arbitrary number of subpartitions? Okay, so the original strategy was to consider, well, to consider what are the geometric objects in this entropy space that are relevant. Okay, so first of all, we don't need to consider just sign definite quantities like mutual information or conditional mutual information, but also a broader set of quantities, so-called information quantities, which are just objects that are composed from, you know, linear combinations of these subsystem and entanglement entropies with some integer coefficients. Okay, and you can, which can be positive or negative. So, for example, this mutual information would be, you know, this would be 1, this would be 1, and this would be -1, and the whole rest of them would be 0. So now we can generalize this to arbitrary, you know, set of coefficients like this. So that's some what we call information quantity, and we're interested in ones which can vanish without the others vanishing, meaning which can be described by, well, physically they're sort of characterizing some independent, you know, correlation measure, multipartite correlation measure, but geometrically they are described by a hyperplane in the entropy space. They provide one relation that can be saturated with none of the other relations being saturated, meaning it's really a codimension 1 object, a hyperplane. Okay, so these information quantities are objects which, when vanishing, define a hyperplane, or well, when evaluated to anything, define a hyperplane. So these hyperplanes for these vanishing information quantities then specify a mathematical construct, which is this hyperplane arrangement. And that's a convenient construct for us to characterize the entanglement structure for these states. Okay, the second important ingredient was to utilize holography. And there are two key aspects to this. One is simply the holographic entanglement entropy prescription, which of course you all know very well, but the thing that I want to highlight here is that, well, it's given, well, in the original RT or HRT context, it was given by minimizing over a certain set of, the area of certain set of surfaces, okay, in the full general, covariant context, it's the extremal surfaces. So I take my boundary region, I consider the set of all extremal surfaces that are homologous to this region. Okay, there can be multiple ones in principle. Okay, but I take the least area one out of all such homologous extremal surfaces. Again, it's this minimization that allows for phase transitions. And that's sort of one of the key characteristics or key properties that this holographic and entropy cone is utilizing, or our description of the holographic entropy cone is utilizing. Okay, so just to specify what I mean by this allowing for phase transitions, you can imagine, let's say we have some composite system like this, and we want to understand entanglement entropy of the joint subsystem AB. Well, you might have an extremal surface that's really these two extremal surfaces, or you might imagine that as you bring these regions close enough, that there's another extremal surface that exists, and that might actually have smaller area than these two, which is this joint extremal surface. So there's a phase transition on what is the smallest area extremal surface that is homologous to the subsystem. All right, so that was one ingredient. Another ingredient, which is which motivated us to use to arrive at a present formulation, is the following. So I've been glibly talking about entropy vectors for holographic subsystems without really telling you, or with shoving under the rug, the fact that generically these things are infinite. Entropy of any subsystem with an entangling surface is infinite because that, okay, this is the boundary, this is the bulk, the extremal surface ends on the boundary, meaning it has infinite area. And so there's this UV divergence in the entanglement entropy. So entanglement entropy of A would be infinite, entanglement entropy of B would be infinite. And you might think that, well, maybe we can work on somehow the celestial sphere of the entropy space, but even that's not quite the right construct, because the ratio of these depends on, so you can make them finite by taking some cutoff, but because we can specify the cutoff to be, position dependent, even the ratio of these things depends on how we take away the cutoff, what sort of cutoff we specify. So it's not quite we can't quite work on just the celestial sphere of the entropy space either. And so, okay, we can work at some finite cutoff to get some finite entropy vector, but then it's cutoff dependent. Okay, so what do we do? Well, the observation is that there are nevertheless information quantities which are cutoff independent. And one example of that is this mutual information, where you see if we have these systems decorrelated so that mutual information is vanishing, then it doesn't matter what sort of cutoff we take, because after all, S of A is computed by whatever this part of the surface is, S of B by this part of the surface, but S of AB is computed by this plus this. And so no matter what cutoff we take, those pieces just cancel identically. And so what that means is if we associate to the components of the entropy vector, the S of A, S of B, and S of AB, finite numbers that we can wiggle around by wiggling around this cutoff, that set of entropy vectors is not allowed to live in an open in some codimension 0 region in the entropy space, but only a subspace given by this relation. It has to be a subspace where this mutual information vanishes. Okay, and so that subspace, in this case, if you have just one such relation, it's just a hyperplane. That hyperplane is the thing that most naturally corresponds to a configuration like this. It's not a single vector or single ray. It's really a subspace delimited by all these information quantities that vanish. And so now we can recast.
I have a question.
Let me just finish the sentence. So,
okay.
And then I'll let you ask your question. So we can recast the entanglement entropy in terms of not areas of the surfaces, but rather in terms of what we call a proto-entropy, and associate that quantity with the extremal surfaces themselves, not their areas which diverge, but really the surfaces. Because after all, in a quantity like this, it's the surfaces that effectively get subtracted to get 0. And so that's sort of the key observation, is that we can now work with these constructs, with these abstract constructs, rather than worrying about the actual values of these areas, which are infinite, work with these proto-entropies, and everything then reduces to combinatorics. We no longer care about the, if we wiggle the surface around a little bit, okay, its area changes, but that's okay, because we don't care that that area numerically changes for some cutoff, but rather that surface was utilized by maybe S of A, maybe also S of AB, but maybe not S of ABC. Okay, and it's the combination of which composite subsystem utilizes that surface that delimits the full quantum entropy cone, and therefore allows us to translate the problem of finding the boundary of the entropy cone to just combinatorics, rather than a problem in geometry. Okay, I can now pause for the questions.
So when the phase transition occurs, when S of AB is no longer given by S of A plus S of B, then this cutoff dependence comes in, right? Comes in back.
It comes back, but we don't care, because the cone is going to be delimited by the facets which correspond to vanishing mutual information, not the positive one, but the vanishing one. So the cutoff will influence what's inside the cone. It's not going to influence what's on the boundary of the cone. And because we're delimiting the cone by its boundary, we no longer care about the cutoff dependence. So that's the trick.
Okay.
Okay, good. So, okay, so now I can, so that took a long time. So let me try to go a little bit faster. So let me introduce these two geometric constructs. One I already hinted at, which is this Vspace. Okay, this is a subspace of the entropy space, which is given by the intersection of all these hyperplanes specified by vanishing information quantities, these primitive information quantities which vanish. Okay, and depending on how many independent ones you can have dimensionality anywhere from the full dimension of the entropy space, of if there's no such thing that vanishes, to just one-dimensional thing if there's d-1 such independent information quantities that vanish. Okay, so this Vspace is just some linear subspace. Now, for each configuration and state, there's a unique such Vspace that's associated to it, as we saw previously in this picture. There would have been a Vspace that's a hyperplane of just vanishing mutual information. More generally, you have different perhaps lower dimensional Vspaces, and it's the object that captures these essential features of this entanglement structure. As we were saying just a moment ago, the numerical values of entropies don't matter. It really matters structurally only which ones of these vanish and which ones of these don't yet vanish. And so in some sense, it's the most refined, it's an extended object, but it's the most localized, meaningful geometrical object associated with a configuration. Because the entropy vector is really this infinite object. It's not meaningful, but there is a object which is meaningful, which is this Vspace. Okay, so that's that. So you should think of, to every configuration, there's associated not just an entropy vector, but a full subspace. Okay, and that subspace, there's only a discrete set of those things. Okay, so, and it's a unifying construct because it unifies these extreme rays, which would be one-dimensional Vspaces, or these facets, which would be d-1 dimensional subspaces. So depending on whether your configuration corresponds to an extreme ray, or maybe as a generating configuration for one of these facets, or maybe as some intermediate thing, that gives the dimensionality of the Vspace. So that's nice refined quantity, but it depends on specifying all of these primitive information quantities. Now, there's a much more primitive construct, which is a subset of these that we have already seen, in particular, just the mutual informations. Okay, that subspace, that quantity is labeled, is what I'm calling this pattern of marginal independence, PMI, and it's a specification of which just mutual informations vanish. Okay, it's called marginal independence because these reduced density matrices are called marginals, and if they're independent, that means that the total density matrix is a product of these reduced density matrices, so that the mutual information vanishes. Okay, so marginal independence refers to vanishing mutual information. And we want to ask which of these mutual information between any composite cis subsystem and any disjoint composite subsystem can vanish simultaneously. So that each of those vanishings specifies a hyperplane, and now we're on this intersection of these hyperplanes. So again, each entropy vector would have a unique such pattern of marginal independence, unique set of mutual informations that are zero, but it's a more primitive construct than the Vspace because we're only caring about these mutual informations and not about other information quantities. And so in particular, it's a subspace which contains the Vspace because Vspace was given by intersection of all these guys plus other information quantities. Okay. But we want to ask more specifically, well, what exactly, apart from this inclusion, what is the relation between the Vspace and PMI? And in general, that's a complicated thing. We'll find a context where it's very simple, where they coincide. Okay, so those are two geometric constructs. I should say that this pattern of marginal independence, specification of which patterns are actually allowed, is a very important problem in quantum information. It's called marginal independence problem. And just to motivate why not all possible patterns can be realizable, can exist, correspond to some physical states, there's two basic types of things that prevent you. One type is mathematical inconsistency, and another one is sort of physical inconsistency. Mathematical inconsistencies, things like identities that would get violated. So here, if you use the fact that the tripartite information is symmetric under permuting its arguments and write that out, you get an identity like this. Or you can just brute force write this out in terms of the entropies and check that this is just equal to this, okay, for any subsystems A, B, and C. And so if the pattern of marginal independence says that this is zero, and this is zero, and this is zero, but that this is not zero, well, that can't happen. That's just totally inconsistent mathematically. Okay, so one thing we want to, this problem addresses is how to find all such relations. The other type of inconsistency is a physical one, that it violates some of these physical requirements, these relations like strong subadditivity or subadditivity. So for example, strong subadditivity said, if you have a composite a correlation between composite subsystem vanishing, then it has to vanish for a smaller subsystem. Okay, this is this monotonicity under inclusion. Well, so if you see that this one, if the pattern specifies this one being 0, but this one being non-zero, well, that's problematic because that would violate this SSA. Even more simple example would be just SA. So here we could say, well, this is 0, but these two are non-zero. That violates SA because even though that doesn't violate the identity if this was positive and this was negative, knowing that they can't be negative means that they also both have to vanish if these two vanish. Okay, and so forth. So figuring out this answer, well, let me again finish. Answer to this problem is, again, depends on what subsystem you're taking. The quantum marginal independence problem, we sort of started describing in this work. What we're interested here in is the holographic marginal independence problem, namely which patterns of marginal independence are realizable holographically. And what I want to build up to, which I don't have very much time to do, is that in fact, the solution to this problem gives us an in principle construction of the entire holographic entropy cone. Okay, so well, okay, so go ahead, you can ask.
Yeah, so mutual information, if we take into account 1 over n correction, mutual information can be non-zero, even though holographic classical gravity dual has a 0 value. So the quantum correction maybe changes the structure of cone.
Mm-hmm.
Yeah, structure of cone about PMI.
Indeed, so if you have quantum correction, so in quantum field theory, you don't, on connected space, you don't really decorrelate systems. It's bounded, mutual information is bounded from below by a correlator, which is non-vanishing, but it's subleading in n. So we're taking the infinite n limit here, which is what allows us to, which is much simpler situation where we really can reach all these facets. So in quantum field theory, we might not reach really all the way down to all these facets, which is a complication, but it doesn't matter because we could then consider, CFTs, set of CFTs living on, disjoint spaces and so forth. But here we're just taking a simpler context where we can reach all these facets. Does that answer the question?
So can we kind of systematically understand also 1 over n correction to entropy cone?
That's an excellent question. So we haven't thought about that very much. One can, so certainly you might get, you will get something that's in principle, well, the full quantum, it should converge ultimately to the quantum entropy cone, okay, which is strictly larger than the holographic entropy cone. However, so for example, you can violate MMI with finite n and so forth, but at the same time, it's sort of a bit more complicated because of this not reaching these subadditivities, vanishing and so forth. So you have to consider more complicated systems that can be decorrelated to reach all of those regions. But it would be very interesting to explore maybe perturbatively how the cone gets deformed in 1 over n corrections or things like that. But that, we haven't done any of that.
Changing if we take into account 1 over n correction.
It should be changing.
Yeah, and it's smoothly changing.
Smoothly. Well, yes, it should be smoothly changing. That's almost by, I mean, yeah, that's sort of almost by definition. There isn't anything, I mean, the entropy itself is smoothly changing in 1 over n.
I see.
So
thank you very much.
Great.
So how is the bulk gravity going to emerge from all this?
Well, good. So let me try to build up to that. Okay, so let me speed up. Okay, so let me, I will actually, because actually, how much time do I have? Let me just ask.
Yeah, I think 10 minutes or 10 or 15 minutes.
Okay, very good. Okay, so let me quickly indicate just briefly sort of two tools that we use to get to this sort of the main result. One is using graph models, which sort of explicitly discretize the structure, which was already used in this original holographic entropy cone paper. And there the trick is to associate to any, so you take your bulk, which is now take all the set of the relevant RT surfaces. Now we're only restricting to static situations, so that we're using just the RT prescription where this graph model can be implemented. And we partition the bulk by regions that are defined by these RT surfaces. And to each region, we assign a vertex, and to each surface, that part of a RT surface that separates those regions, we assign an edge. So just to exemplify this, if we have a configuration like this, we have a vertex for this region inside here that we call A, for this region inside here that we call, that's this vertex B, and everything else, that's this other vertex, that's sort of the purifier. And there's two surfaces, which are these two edges. A more complicated thing would be where you have a region near A, a region near B, and the region that's sort of inside this surface and everything outside. So then you get an additional edge for this surface. Now to each edge, you assign a weight that's given by the area of that part of the surface. And the entropy is then computed by sort of the minimal cut of this graph where you sum up the edge weights. Okay, so that's a framework that you can use to get the model for this holographic entropy, holographic setting in much more discrete, simpler systems. But it turns out that the cone for these graphs, for all graphs that you can get that way, coincides with the RT cone that was argued by these folks. Okay, so we can study the holographic entropy cone using such graph models, and you can then basically the exercise boils down to specifying what is sort of the mean cut structure. Is it that that the entropy of AB, for example, here is given by the sum of these, which would be this type of cut, or just this surface, which would be this type of cut. Okay, so we can analyze this in this graph configuration. Now, if you have lots of correlations between subsystems, the graphs get complicated very quickly. So here I have 4 regions rather than 2, as was in my previous case, which are pairwise correlated with everything. And so the number of these bulk regions that it specifies, that it separates, is really this these 43 different vertices, because this arch between B and D contains the intersects maybe the arch, 3-way arch between A, C, and B, and so forth. Okay, so there's all these intersections, and it's a complicated mess. Okay, so they would not be very useful, but there are simpler graphs which are very nice, that behave very nicely. And those graphs are so-called tree graphs. They don't have any of these cycles. And in fact, tree graphs which are simple are ones where each edge is homologous to some subsystem. So for example, this edge you can think of as forming a cut for this BC subsystem. This edge is forming a cut for this composite, D, E, F, G, H, I, J subsystem, and so forth. So each edge has its own subsystem, and that provides an enormously simple, enormous simplification. Okay, so the theorem that's very easy to argue is that for such graphs, this Vspace is in fact the PMI, meaning that any sort of entropy relations that we can get are described by relations between these various edge weights. But because these various edge weights correspond to entanglement entropy of some subsystem, such relations all boil down to relations of mutual information vanishing. And so all the relations we get that specify the Vspace, in fact, are of the form of vanishing mutual information, and therefore are this PMI. And so that means that if we get a one-dimensional Vspace, that would be an extreme ray described by such a simple tree graph, then we're guaranteed that this is a one-dimensional pattern of marginal independence, namely an extreme ray of a cone that's specified just by subadditivities, which is a subadditivity cone, a larger, sort of the largest cone that's a nice geometric object to define. Okay, so these simple tree graphs will play a very key technical role. Now, I said that, well, simple tree graphs are nice, but what does that have to do with the configurations that we're interested in? So here's the sort of the main conjecture that we have lots of evidence but haven't proved, on which the main result is based, on which the main result assumes. The conjecture is the following. The conjecture is that we can convert any holographic graph model, or really what we need is just extreme ray graph, into a tree graph while preserving the Vspace, or even preserving the entropy vector. So here's a simple example. You can have a graph with a cycle in it like this. That's not a tree graph, but its entropy vector is equivalent to the entropy vector of a tree graph. Okay, so this would be this conversion where we sort of zip up these edges to look like this. So you can check very easily that, well, entropy of this boundary subsystem is, A plus B, which is this leg and so forth. Okay, so you can do that. So you can show that for large set of such generic graphs, you can explicitly convert it. You can check that for all the known extreme rays, holographic extreme rays, you can always convert it to a tree graph. Okay, so that, but not necessarily a simple tree graph yet. So here are, this is the set of the extreme rays for, yes?
So when you're talking about these tree graphs, you really mean systems where the phase transition has occurred, because you said that the tree graphs are formed by the wormhole connecting to
No. This is just, forget about phase transitions. This is, okay. The phase transitions are specifying different min cuts. Okay. Here, I'm just specifying the topological structure of the graph. Okay. And the phase transition would correspond to saying, say, this min cut, now it becomes this min cut. Okay, that's a phase transition.
No, so
I'm saying here is that I can describe my graphs. Okay, I can convert my graphs, even complicated ones like this that correspond to some holographic configuration, into something that actually collapses all these different cycles and becomes a tree graph. On top of that, I can then specify, what type of min cut structure I have, but I can abstract, because once I have shown that the holographic cone is the graph cone, I no longer have to worry about, which min cut structure a given configuration has. I can just work now with a set of all graphs and ask what is the cone for that. Okay, so that's the idea. Okay, so here I have abstracted myself away from worrying about the phase transitions. I'm just telling you that these tree graphs have the property, well, simple tree graphs have Vspace being PMI. Now I'm saying that I can actually convert graphs corresponding to extreme rays of holographic entropy cone into tree graphs. Okay, so here there are some that have cycles, but you can undo the cycles while preserving the entropy vector. And so ultimately, you do get, well, some of them already are tree graphs, some of them are not, some of them are trivially converted by sort of taking this single boundary vertex and making it into multiple boundary vertices, and some are slightly more complicated. But what you end up with is all trees, but some of them would have, if I resolve these boundary vertices, then I have multiple regions, multiple boundary vertices of the same color with the same label. So that's not a simple tree graph. So the next important step is to convert it into a simple tree graph. And that happens with the process of fine graining. So that all is achieved by considering what happens when instead of some number n of partitions, we have some different number, let's say n prime of partitions. Okay, that changes the dimensionality of the entropy space. But there are still some aspects of these entanglement structures that are inherited between the two. So if you increase n, so n prime is greater than n, then that corresponds to fine graining. If you decrease it, that corresponds to coarse graining. So coarse graining has the effect of saying, well, you have multiple boundary vertices that were different labels, but I might not distinguish between them. And so I call them the same label. Okay, so multiple colors are indistinguishable. That has the effect of projecting the entropy vectors from this larger space into this smaller space. Conversely, I can fine grain to declare that things that have the same label, different vertices that have the same label, actually are different, should have different labels. So instead of having one vertex for, two vertices for A, I call this one for A1, this one A2, and I declare A1 is distinct from A2. Okay, so once I do that for these non-simple tree graphs, I can just convert them into simple tree graphs by saying each vertex is a different color. I have fine grained. And now I'm in business because now I can use this PMI being the Vspace. Okay, so here's the main result. Here's the main result. The main result is the following. So consider some n-party holographic entropy cone. That is a convex hull of its extreme rays. Okay, so in principle, once I can describe how to find these extreme rays, I could describe for you how to find their convex hull, and that would define for me the holographic entropy cone. So what are these? So how do I specify these extreme rays? Okay, so assuming that each graph corresponding to extreme ray can be changed into a tree graph, I can show that any extreme ray of this holographic entropy cone, in fact, is nothing but a projection of an extreme ray of just a subadditivity cone, a cone specified just by subadditivity relations, none of the other more complicated holographic relations, but just this simple subadditivity for some larger number of parties. Okay, so the basic idea of the proof is to say, well, we start with this extreme ray for the n-party holographic entropy cone. We get some graph representation. That graph representation has one-dimensional Vspace. Now we use the conjecture, convert it into a graph that's a simple tree in some higher party, in some fine-grained entropy space. Okay, so this is now a simple tree graph for which we have the Vspace being PMI. This might now have enlarged the dimensionality of Vspace, but we can maintain the same extreme ray in such a way that we get a one-dimensional Vspace and therefore one-dimensional PMI in this higher dimensional entropy space. But PMI means this pattern of marginal independence being one-dimensional means that you have d prime minus 1 different mutual informations that vanish, meaning this is an extreme ray of the subadditivity cone. And so that's an object that we can define without knowing anything about holography. And the statement is that now that original holographic entropy cone extreme ray is obtainable from projecting down back to this ended party space, this extreme ray for this just sub-additivity cone. Okay, so this is the implications of the theorem then is quite surprising at first sight, because we're saying that the holographic entropy cone is really determined by just sub-additivity cone for some refined system. Sub-additivity cone really doesn't know anything about holography. It just says that correlations can't be negative. Amount of correlation can't be negative. That's true for any quantum system, not just holographic ones. And yet, okay, that knowing the right set of extreme rays of this sub-additivity cone allows us to take the convex hull of their projection to this n-party space, and that convex hull specifies this holographic entropy cone. And so similarly, all the higher dimensional faces and the internal structure of this holographic entropy cone are just obtained by these projections of the sub-additivity cone. And so that means that this complicated multipartite entanglement structure really is just encoded or rooted in this pattern of marginal independence, which subsystems can be simultaneously independent of each other, decorrelated from each other, and nothing else. But and I should say, as another throwaway remark, very curiously, you can also show that because these other holographic entropy cone facets, which are not sub-additivities, have a certain property called superbalance, they are not monotonic under inclusion, and so they're not natural correlation measures. But nevertheless, you're obtaining all of these facets indirectly from just correlation measures, in particular the mutual information. Now, this is a bit, abstract. In practice, it's a complicated procedure to, first of all, get the correct set of extreme rays for all, sufficiently high n prime. Then you have to project, you have to take the convex hull, and then once you have the extreme rays, you want to recast the cone in terms of the facets to extract the inequalities. So that's a complicated problem. I mean, it's computationally hard problem, but nevertheless, conceptually, it sort of points to where the cone is. I mean, somehow, what is it in holography? What is the key aspect of this holographic relation? Now, I put the star here. I haven't gotten to the star. This fully specification or full determination requires me to tell you which of these extreme rays of this full cone I'm supposed to be taking. Okay, and that's the important problem. We haven't solved that, but the solution to that problem, I claim, is precisely this. Is once I solve it's less than it's more easier than the solution to this holographic marginal independence problem, in the sense that holographic marginal independence problem gives us more than just that answer if we solve it. So the observation is that certainly we can't take all the extreme rays because of the sub-additivity cone, because some of those extreme rays are not even physical, are not quantum states are not reachable by quantum states. In particular, they can violate SSA. Okay, so so all extreme rays are no good. So we have to take some subset. And so the set that we want to take is the set which is holographically realizable. So the question is, what is the set of holographically realizable extreme rays of sub-additivity cone? Okay, so one conjecture is that anything that's compatible with quantum mechanics, any extreme ray compatible with quantum mechanics, is in fact holographic. It's realizable by holographic configurations or equivalently realizable by graphs. Even though not all states that are quantum mechanical are realizable in holography, but just the extreme rays might be. Okay, so that's a conjecture. Speculation is that you can get that set, you can describe that set by all extreme rays that just satisfy SSA. again, the quantum entropy cone is delimited by more than just SSA, but nevertheless, it can be that the extreme rays that are consistent, that are consistent with sort of quantum mechanics are, you only need for them to be consistent with SSA, and that automatically gives us the right set. If both of these are true, then the corollary would be that it's just the extreme rays of the subadditivity cone that are holographic, which are what we need. Okay, but that's still work in progress. So since I'm out of time, I will just stop here and thank you for your attention and invite questions.
Thank you very much for a very interesting talk. So are there questions or comments?
Please.
So Matt, Matt, please ask.
Thanks for the nice talk, Veronika. I'm just curious.
Thanks for setting it up for me.
I don't know if you saw this paper a couple days ago by Bartek Czech about the symmetrized holographic entropy cone.
Right.
And I was just curious if you had any comment on, I mean, that's also a speculation for some way of understanding the structure underneath the holographic entropy cone. So is there any connection, any obvious relation to your point of view on it?
Right, so let me go back to some picture of this. There's a better way to do this, which, okay, I'm almost there, I think. Okay, let's take a picture like this. So what they're considering is a subspace of the entropy space. Actually, maybe I should just go to the entropy space. So in a quantity like, let's say, where we have 3 parties, the entropy space is 7-dimensional, but you can consider a subspace of it, which is lower dimensional, where instead of taking all of these different axes, we take fewer axes that are combinations. So we can take a symmetric combination that's fully permutation invariant by considering S of A plus S of B plus S of C plus S of A, B, C divided by 4, let's say, to normalize it and describe that as one quantity. And then we can take another axis, so that's one axis. Another axis is S of AB plus S of BC plus S of AC divided by 3. That's another permutation, fully permutation invariant quantity. And that's it. For n equal to 3, there's nothing more. But in this subspace, now 2-dimensional subspace, we can then convert these relations like this by just replacing each of these guys by the average under all the possible permutations. And so we would get something like, the first quantity, twice the first quantity is greater than the second quantity, or here the MMI one would be like, 3 times the second quantity is greater than 4 times the first quantity of these, for these average things. Now, that's a very coarse-grained picture. And it does give, okay, so the advantage of it is that you can define these coarse-grained cones very explicitly, okay, but it's a exponentially small subspace of the entropy space. So it's not fully clear to me what really to extract from it. In other words, the things that we already know about the holographic entropy cone, seem to be more detailed than what you can say from these from bounding these average quantities. So I haven't, but yeah, so I don't really have much to say about any sort of relation between the SA cone that we're examining and in this now much larger space, and this severely reduced sort of what do you call it, symmetrized entropy space.
Okay.
But it's an interesting direction. It's another thing that indeed one can do. One can have this. I mean, we know that the full cone is symmetric under permutations and purifications, but that's not like by averaging it, you're sort of squeezing it. It feels like you're squeezing it a bit too much. You really want to retain. I mean, it's symmetric under the permutations, but what you have done is just consider the symmetrized quantities, whereas we know that the individual relations like this are not by themselves symmetric. It's just that the whole set of them is symmetric. And so it loses all of these except for the fully symmetric ones, and that's just a sort of trivial subset in some sense.
Right. Okay, thank you.
Okay, so Tadashi, can you ask?
Yes. Can I ask a question? So you have very nice relation between the subadditivity cone and the holographic entropy cone. And so subadditivity cone has an n prime number. And n prime is some simple function of n? Or are there some systematic?
No, it's not a simple function of n. In fact, we don't know what function it is. I think it's bound. I mean, it's so for n equal to 4, n prime is just 4. For n equal to 5, I think it's slightly larger, but not much larger. But as far as universal bound for arbitrary n, n prime can be much larger. So it could be exponentially larger. It might even be doubly exponentially larger. But there is a bound. Okay, so it can be more than doubly exponentially larger. I think that we can show, but that's a very weak bound.
I see.
But the philosophy is, so it's not okay. So it's not that we would extract the holographic entropy cone explicitly by this procedure, because even describing the subadditivity cone explicitly is complicated. Once you get past n equal to 6 or something, it's terribly complicated. But it's more a conceptual statement that it really is just rooted in what sets of subsystems can be simultaneously decorrelated, which is much simpler problem. And you might imagine that you can find an answer that's actually, without specifying it explicitly, that's suggestive. So already one bit of an answer to this is, let's see if I can, oh no, I think I know how to go back and forth. Okay, I had my pointer and that was the problem. So the answer to, part answer to this question is the following. So we know that the only extreme rays that can be possibly relevant are of the subadditivity cone are those that are lying on the boundary of the first sets that correspond to vanishing mutual information between the single, what we call monochromatic subsystems, not composite ones. Because if you have let's say, mutual information between A and B, C vanishing, which would be one of these other facets, then it can't happen without mutual information between A and B vanishing. And so you would no longer be on a facet. And so that means that you have only, out of these many different possible facets, which are like Stirling numbers worth of facets, you have only n choose 2, much smaller set of extreme rays that could possibly be relevant. What we don't know yet is if it's all of them or if it's still some subset of them. But that's already a severely restricted set of these extreme rays that are relevant. But nevertheless, so that's a geometrical statement that we could say for any n. But nevertheless, even though we can say that geometrical statement, finding it explicitly, like describing that collection of extreme rays in this large dimensional, exponentially large dimensional entropy space, that can still be complicated.
Thank you very much.
Jonathan Harper, please.
Hi, Veronika.
Hey.
So your main result here was focusing on mutual information, or in the K basis, the K2s. So I was wondering if you guys had thought any about similar results for K4, K6, etc. Namely, we could imagine some nice world where instead of the entropy cone we were handed, we had essentially positivity of the K4s and K6s. And you could consider like doing some similar analysis to what you did here. So I was just kind of curious if you guys had thought any about that or similar ideas.
Well, we have, so indeed, so you can express an entropy vector in different representation. Rather than collecting entropies, you can collect multipartite informations or these perfect tensor K basis objects. And indeed, it's useful, very useful representation. For one, if you look at this, let's see, I had some appendix somewhere. Okay, I don't know whether this is very visible, but if you write, so these things that you're referring to, these K basis objects would describe these different inequalities in a form that's sort of much more compact. So the first line, always the white line, is in entropy representation, and the other ones are in the multipartite information or in the K basis, and they're more compact. So already that's suggestive that somehow the K basis is, or the I basis is better. Now the K basis has the advantage that it's manifestly purification symmetric, whereas the I basis is only permutation symmetric. It turns out that it sort of loses its advantage at large enough n. So we have been playing with that, especially with Sergio and my student Frederic Gia. We had played with that quite a lot, but we haven't really we haven't really found, you might imagine that there's some phrasing of these in terms of these inequalities that is very natural in these representations, that the negative for what these inequalities are telling us, or the way of generating them, is somehow much more suggestive. Okay, so that was our hope, and we sort of explored it a little bit, but so far we don't really have. So far, it doesn't seem to give any particularly compelling narrative. In fact, we can find representations of these inequalities that are even more compact in terms of various conditional quantities, but even there, it's not sort of clear what the narrative really is. But I think that's. But I think that would be. That is useful, and especially in the context like your work of these hypergraphs and so forth, various statistics that could be a definitely interesting direction for exploring.
Right. No, I guess part.
Go ahead.
No, I was just going to say, you could imagine a world where, as I said, like K4 and K6 were strictly positive, and then all of the structure just basically collapses down to the positivity of the Ks. And in which case, then this similar story that you had for, the mutual information, you could try and play similar games. So maybe there's some nice way of understanding the difference between the actual holographic entropy cone and this like nice subset of the holographic entropy cone, where this additional structure, you might be able to like try and understand the differences of how, the fact that we only have positivity of the K2s is somehow leading to this like different and richer structure.
Right. Well, the positive, okay. I mean, one thing that's sort of related is the superbalance property, that all the holographic inequalities that are not subadditivities are, if you write them in this, well, either in terms of the case or in terms of the i's, you never get, I2s or K2s, you only get higher case. In terms of the case, they always have positive coefficient. It doesn't mean that they themselves are positive, but the coefficients in there are positive. And similarly, in the I basis, the coefficients always alternate depending on, how many arguments it has, whether it's even or odd. So that at that level, those two are on equal footing. But that's one remark which is related, but I don't really have a nothing more.
Sure, no worries. Thank you.
Okay, so since we are behind the time, so why don't we postpone the remaining discussion to the coffee break after the next talk? And yeah, so Tadashi, do we need 5 minutes break or so here? Or
maybe a few minutes break?
Yeah. So shall we start at 11:35 or something?
Yes, I think that's a good idea.
Yeah, okay. So let's take 4 minutes break and come back at 11:35. Thank you very much, Veronika.
Thank you.